My name is Itamar,
And I'm Jonathan.
and this is our project about Fourier series. So Fourier series allows us to represent any wave or periodic function as a series of sine and or cosines. This can be used in a variety of applications, one of which is noise cancelling headphones. As demonstrated by the picture, these headphones detect sound waves and generate an anti-wave, which is a wave that is 180 degrees out of phase, to cancel the sound. This process uses Fourier series to break down the incoming complex sound waves into simpler sine or cosine waves, allowing the anti-wave to be generated easily. As I said in the last slide, a Fourier series models periodic functions through the sum of sines and cosines. So a periodic function f of t equals a of 0, which is a constant, plus a of 1 times cosine of t, plus b of 1 times sine of t, plus a of 2 times cosine 2t, and so on. In this presentation, we will use a Fourier series to represent the square wave function, which has a period of 2 pi. So how do you get from the equation to the square wave function?
Well, Itamar, nice of you to ask that. You gotta do a lot of math here and here, and then you gotta use the math that you just mathed here to put in here, 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 and here. Got it? I know you didn't, because I didn't either, until my Lord and Savior Salcon descended from the heavens to gift me the forbidden fruit of knowledge. But Sal wasn't here, so you gotta put up with me. So here's my rough take on it. You have two fundamental equations, here and here. The integral from 0 to 2 pi of sine mt for any integers of m, and the integral of 0 to 2 pi of cosine mt for any non-zero integers of m. I'm going to call these the elements of the Fourier series. So after you derive these two equations using some sick cool maths, you then plug these into the other 5 equations using trig identities, which look like this. You first expand these 5 integrals using the trig identities, and then you plug in the first 2 integrals into those 5 equations, and then boom, you did it. Now, armed with so much knowledge, we could plug this back into the equation we had in the beginning and integrate it. Now, when integrated, all but 1, our first number, will become 0, making it easy to isolate our coefficients and find our general equation. Take it over, Itamar.
Our formula for a of n is 1 over pi times the integral from 0 to 2 pi of ft cosine nt dt. And again, we can split the integral into 2 other ones, one from 0 to pi and the other from pi to 2 pi. And because the second integral equals 0, we get that a of n equals 1 over pi times the integral from 0 to pi of 3 cosine nt dt, which then equals 3 over pi times sine nt over n, evaluated from 0 to pi. And because the sine of any multiple of pi equals 0 and the sine of 0 equals 0, we get that a of n actually equals 0. And this means that the series for the square wave function doesn't contain any cosines. So the formula for b of n is 1 over pi times the integral from 0 to 2 pi of ft sine nt dt. And using a similar method to the one we used in the last slide, we get that b of n equals 1 over pi times the integral from 0 to pi of 3 sine nt dt. And then taking the antiderivative, that equals 3 over pi times negative cosine nt over n, evaluated from 0 to pi, which can be simplified into negative 3 over n pi times cosine of n pi minus 1. And cosine of n pi minus 1 will equal 0 when n is even, and negative 2 when n is odd. So b of n equals 0 when n is even, and 6 over n pi when n is odd. So now that we know that a of 0 equals 3 over 2, a of n equals 0, and b of n equals 6 over n pi when n is odd, we can finally find the series for the square wave function. So the first 4 terms of the series are 3 over 2 plus 6 over pi times sine t, plus 6 over 3 pi times sine 3t, plus 6 over 5 pi times sine 5t. And the general term is 6 over 2n minus 1 times pi times sine of 2n minus 1t. And we can also write that using sigma notation, and we get that 3 over 2, that f of t equals 3 over 2 plus the sum of 6 over 2n minus 1 pi times sine of 2n minus 1t starting at n equals 1. So we were able to graph our function on Desmos using the sigma notation from the last slide, and you can see how every additional term as k grows from 0 to 7 makes the graph look more and more like the square wave function. And this is what the graph looks like at 100 terms, so pretty close to the square wave function. And that's it, so thank you for listening.